In this video, I stated two fundamental theorem of integral calculus. It gives the relation between definite integral and primitive. I explain how it gives the relation between definite integral and primitive. Now, theorem statement is like this: if integral a to b f of x dx exists, and there exists a function pi. There exists a function pi such that pi dash is equal to f. Then integral a to b f of x dx is equal to pi of b minus pi of b. Now, in the last video, I explained what is a function defined by definite integral and what is primitive. Now, this pi is such that pi dash is equal to f. This pi is called nothing but primitive. First, I explain the proof of this theorem, then how this theorem is important. I explain how this theorem is important. This theorem is used for practical purpose. To solve the problems, this is very helpful, this theorem. Proof is like this. What is given here? Given f is equal to pi dash. F is equal to pi dash is bounded and integrable. In AB. Now, by definition of Riemann integral, what does this imply? This implies there exists a division D. We take the division as x0, x1, etc., xr minus 1, etc., xr and xn is equal to b. This is the division of AB such that mod of sigma r is equal to 1 to n pi dash xi r into delta means xr minus 1 minus a to b pi dash x dx is less than epsilon, where xi r belongs to xr minus 1 xr. This is, we have used here alternate definition of Riemann integration. We had given two definitions of Riemann integration. First one is in terms of sums, upper and lower sums. Then we have defined alternate definition of Riemann integral. I have used this. You refer that one. Alternate definition of Riemann integration. I take this as 1. I have to refer this. So take this as 1. Now I apply for this pi dash xi r, I apply the differential calculus, mean value theorem of differential calculus. What does that theorem states? Again, there are two forms in mean value theorem. Well, the first form is like this: if a function fx is continuous in closed interval AB, differentiable in open interval AB, then there exists C belongs to AB, open interval AB, such that f of b minus f of a upon b minus a is equal to f dash c. Do you remember this? This is mean value theorem of differential calculus. Now, another form is there. What is the another form? Suppose function is continuous in a to a plus h. Continuous in closed interval a to a plus h. Differentiable in a to a plus h. Then there exists theta greater than 0 less than 1 such that f of a plus h minus f of a is equal to h into f dash a plus theta h. This is the second form, and we use this second form of the mean value theorem. Now by second form of the mean value theorem, what you get? We get here we apply that second form of the mean value theorem to function pi. We get pi of xr. I explain. Pi of xr minus 1 is delta r into y dash xi r. We apply this theorem, mean value theorem, to pi, because what is the interval here? Interval is, we know that every integral function is continuous, every integral function is differentiable. Therefore, conditions of that mean value theorem are satisfied. So the interval is xr minus 1 xr here. That pi is continuous in xr minus 1 xr, differentiable in xr minus 1 xr, open interval. Therefore, there exists xi r belongs to this xr minus 1 xr, such that pi of xr minus 1 is delta r pi dash xi r. Now I apply this in 1. Therefore, from 1, what do you get? Mod of sigma r is equal to 1 to n, or I write one more step here. I take summation, then I apply this. Take summation. What do you get? Therefore, sigma pi dash xi r delta r is equal to sigma pi of xr minus 1. Did you understand this step? See, it is quite straightforward. This is by applying differential calculus, mean value theorem of differential calculus. Next step, I have taken summation here. Now, what is summation pi of xr minus pi of xr minus 1? This xr minus 1 is xr1 is one subinterval of AB. So summation gives pi of b minus pi of a. Now we apply this in 1. Therefore, from 1, this in place of this sigma pi dash xi r, I substitute. What I have to substitute? Substitute pi of b minus pi of a. It is less than epsilon. Now, what does this implies? Epsilon is arbitrarily assigned positive number. However small it is less than epsilon means integral a to b f of x dx, because pi dash x is fx. Let me write one more step. It is pi of b minus pi of a minus integral a to b f of x dx is less than epsilon, because pi dash is f. This implies integral a to b f of x dx is equal to pi of b minus pi of a. And this is the proof of that fundamental theorem of integral calculus. Important thing is, we have used this mean value theorem of differential calculus. Now, what is the advantage or what is the application of this mean value theorem? Actually, you have used already in practical purpose, in solving problems, you have already used this as a definition of definite integral. Now, while evaluating the definite integral, as I explained earlier, it is difficult to evaluate these simple problems like this, cos x dx, using Riemann integration. It is, however, a tedious process to obtain integral 0 to pi by 2 cos x dx using Riemann integration. But using this fundamental theorem of integral calculus, which gives relation between this definite integral and its primitive. We can easily evaluate. How to evaluate this? First, we find out what is 0 to pi by 2 cos x dx. How to apply this here? First, we find out pi, such that its differentiation is cos x. What is pi therefore? We find out pi here, primitive it is called. We have to find out pi so that pi dash is cos x. What is pi therefore? Pi is sin x, because derivative of sin x is cos x. Therefore, integral 0 to pi by 2 cos x is, by this fundamental theorem, pi of b. Correct? Pi of b. What is pi? Sin x. Sin of pi by 2 minus sin 0. Like this 1. See how simple it is using this fundamental theorem of integral calculus. Let me explain once again. You follow this. By fundamental theorem of integral calculus, what is the theorem states? What does theorem states? If there exists a function pi, so that pi dash is equal to f, then integral a to b fx dx is pi of b minus pi of a. Here pi is called primitive. First we find out pi here. What is given here? Fx is cos x. You have to find out a function pi, so that pi dash is cos x. Fx is cos x. Therefore, what is pi? Sin x. So what is 0 to pi by 2 cos x dx? It is pi of b. Pi is sin x here. Pi of b minus pi of a. So it is 1. That is the application of this fundamental theorem. Now, next topic is, there are two mean value theorems. I prove first one, mean value theorem of integral calculus. First mean value theorem. So from examination point of view, these two theorems are important. Usually, question will be state and prove first mean value theorem of integral calculus, or state and prove second mean value theorem of integral calculus. And there will be some problems on these mean value theorems. Application of mean value theorem. The statement is like this. Suppose integral a to b f of x dx and a to b pi of x dx both exist. Know the meaning of when it exists. And pi x keep the same sign. Namely, positive or negative throughout AB. AB is interval here. Keep the same sign, positive or negative, throughout AB. Then integral a to b f of x into pi of x dx is mu into a to b pi of x dx. What is mu? Mu lies between the bounds of fx. D bounds means supremum and infimum. I explain once again statement. You have to remember the statement also, because question will be state and prove first mean value theorem of integral calculus. What is the theorem? If integral a to b fx dx, a to b pi of x dx both exist, pi of x keep the same sign, namely positive or negative, throughout AB, then there exists mu which lies between the bounds of fx. What are usually bounds of fx we take? Bounds of fx as small m and capital M, such that a to b fx into pi x is mu into a to b pi x dx. This is first mean value theorem of integral calculus. Now I explain proof of this. Proof of this. Proof is like this. What is given? We take small a capital M be the bounds of fx. Bounds of fx. And for definiteness, let pi of x be greater than 0 in AB. What is given? Pi of x is, keep the same sign. First let us take pi of x is greater than 0 in AB. And also m and m are the bounds. Therefore what you get? M is less than or equal to fx, less than or equal to capital M. Correct? Capital M. Now multiply by pi x. M into pi x less than or equal to fx into pi x less than or equal to capital M into pi x. If we multiply, it doesn't affect this less than or equal to, because it is greater than 0. Pi x is greater than 0. So this sign is unaffected. It is not affected. So we can multiply like this. Now we use one corollary here. What is corollary? Corollary of that inequality of definite integrals. So how many times we have used that inequality of definite integral? What is the inequality? M into b minus a less than or equal to integral a to b fx dx. It is less than or equal to capital M into b minus a. Correct? B minus a. Now the corollary is, if fx is greater than or equal to gx, then integral a to b f of x dx is greater than or equal to a to b g of x dx. This is the inequality. Therefore, here, using directly this inequality, integral a to b m into pi of x dx less than or equal to a to b fx into pi x dx less than or equal to capital M into a to b pi of x dx when b is greater than or equal to a. One more is there. It is when b greater than or equal to a. It is. Suppose b less than or equal to a, then what happens? M into a to b pi of x dx is greater than or equal to a to b fx into pi of x dx greater than or equal to capital M into a to b pi of x dx when it is, when b is less than or equal to a. So we have started with this, m and m are the bounds, multiplied by pi x, then you used this. If fx is greater than or equal to pi x, integral a to b fx dx is greater than or equal to, sorry, fx is greater than or equal to, I have taken gx here, a to b fx dx is greater than or equal to a to b gx dx. I think up to this step it is clear. All of you understood this step. It is like this. Now, in any case, whether b greater than or equal to a, less than or equal to a, integral a to b fx into pi of x dx lies between this. What is that? M into a to b pi x dx or capital M into a to b pi x dx. Therefore, there exists mu which is greater than m or equal to m, less than or equal to m, such that mu into a to b pi of x dx. Correct? Pi of x dx. This is when we have taken here pi of x is greater than 0. Suppose pi of x is less than 0. Less than 0. Here you will get less than or equal to. Here you will get less than or equal to sign. But proof is exactly same. Therefore, when pi of x is less than 0, proof is exactly same. So we have proved two theorems now. One is fundamental theorem of integral calculus. Second is what is that? Mean value theorem of integral calculus. Now, if time permits, I take examples based on these mean value theorems. I think it is not possible to consider problems in this video. Let us take problems in next video, and I solve many problems on this, and they are important from examination point of view. Okay, thank you.